everyone, thank you so much for joining this lesson. We're going to be learning about electrode potentials today, and the learning objectives are to use the term standard electrode potential, to look at the techniques and procedures used for the measurement of cell potentials of metals or non-metals in contact with their ions in aqueous solution, and ions of the same element in different oxidation states in contact with a platinum electrode. And then we're going to be able to calculate a standard cell potential by combining two standard electrode potentials. And finally, we will see the prediction of the feasibility of a reaction using standard cell potentials and the limitations of such predictions in terms of kinetics and concentration. We'll also be looking at a required practical, which is measuring the EMF of an electrochemical cell. So in order to compare the tendency of different metals to release electrons, so their electrode potential, we need to use a standard electrode, which we can connect to the other half cell to compare. So our standard is called the standard hydrogen electrode. And there are three very important things to remember, is that number one, the temperature is 298 Kelvin. Secondly, the pressure is 100 kilopascals or 1 atmosphere. And number three is that the concentration of H+ ions in the solution is 1 mole per decimeter cubed. And so what happens in the standard hydrogen electrode is that hydrogen gas is bubbled through the solution of aqueous H+ ions, and platinum metal is used as hydrogen does not conduct electricity. And the key thing with this standard hydrogen electrode is that we define the potential as 0 volts. And that's why we can get the electrode potentials of other half cells when we connect this up to it, because we've defined this as 0. So here we have a zinc half cell set up to the standard hydrogen electrode. And because the standard hydrogen electrode is set at 0 volts, so we've said that it's 0 volts by using it as a standard, that means that when we connect up the voltmeter, the recorded voltage, which is also called the electromotive force, so the EMF, which is the electromotive force, that means this value that we get from the voltmeter is actually the electrode potential of the zinc half cell. In this example, the zinc half cell actually has an electrode potential of minus 0.76 volts. And this means that compared to the standard hydrogen electrode, it forms the relatively negative electrode. So it provides the electrons. And it does this by this process of this equilibrium. And while the standard hydrogen electrode is relatively more positive and undergoes the reduction reaction, which is this. And so overall what happens is that we have this equation. If we combine the two half equations together. If we wanted to write out the conventional cell representation, it would look like this. So we would have the thing that is being oxidized on the left. So that means we have the reducing agent on the left. So zinc is the reducing agent because we're giving away the electrons. And so we would have the zinc half cell on the left. So we would have zinc the solid on the outside because that's the has the small oxidation state. And then we have Zn2 plus in the middle because it's got a higher oxidation number. And then we separate this using double line meaning the salt bridge. And then we have the H plus ions and the hydrogen gas, and also the platinum to choose which one goes in the middle. So the platinum, as a rule, always goes on the outside conventionally. So that means we're picking between hydrogen gas and the H plus ions. And so now we work out the oxidation numbers. So we have H plus, which has an oxidation number of +1, and then we have hydrogen, where the H atom has an oxidation number of 0 because it's an element. And so that means that this H plus goes in the middle because it's got a higher oxidation number. And so therefore we get the H plus, which is aqueous. And then we separate with a straight line because hydrogen is then a gas. And then finally we put the platinum on the outside because it's a solid, and also because we need a solid for to conduct electricity, because hydrogen does not conduct electricity. And we also need a solid to connect up using wires. So now we're going to talk about the standard electrode potential. If we connect up a half cell to the standard hydrogen electrode with these specific conditions, then the electrode potential that we record, so the EMF value, the voltage, can be called the standard electrode potential. So the first condition is that the temperature has to be 298 Kelvin. And then the second condition is that the pressure has to be 1 atmosphere, or that is also equivalent to 100 kilopascals. And then the third condition we have is that the concentration of metal ions is equal to 1 mole per decimeters cubed. And so when we measure the electrode potential, if we use all three of these conditions for our half cell that we're measuring, then we can call it the standard electrode potential. So whatever we record on the voltmeter, that is called the standard electrode potential. And we denote the standard electrode potential by a big E and this symbol at the top. Now, electrodes with negative values of this standard electrode potential are better at releasing electrons than hydrogen, so this makes them better reducing agents. And also, one thing to note is that changing the conditions, such as the concentration of the ions or the temperature, will change its electrical potential. And that's why we have these three conditions that we have to have in order to call it a standard electrode potential. Now we're going to look at how to work out the EMF of a cell. So the EMF is the voltage, and this is obtained by connecting two standard electrodes together and found by finding the difference between the two standard electrode potentials. So we have this equation. The E on the left-hand side stands for the EMF, so that's the electromotive force or the voltage. And this is obtained by doing the standard electrode potential of the right-hand half cell minus the standard electrode potential of the left-hand half cell. And so we'll look at this example. Work out the EMF when we connect an Al3 plus Al electrode to a Pb2 plus Pb electrode. And so first we work out which one goes on the right and which one goes on the left. So we look at this electrochemical series. So we see that Al3 plus is here and Pb2 plus is here. And so we can see that Al3 plus Al electrode, that one's more negative, and so that one goes on the left. So if we were going to draw out the cell representation, it would look like this. We would have aluminium, the solid, and then a straight line, and then Al3 plus, the aqueous ion, and then we'd have the salt bridge, and then Pb2 plus aqueous, a solid line, and then Pb, the solid. And so now we can work out the EMF. So using the equation, EMF is equal to the standard electrode potential of the half cell on the right minus the standard electrode potential of the half cell on the left. And that means that the EMF is equal to minus 0.13 minus 1.66. It's really important to get the signs right and to not forget that you are minusing, but also the standard electric potential could have a minus as well. So the two minuses will make a plus. And this comes out to be 1.53 volts. Another way in which we can work out the EMF of a cell is to draw a cell diagram. So for the example that we saw before of AL3 plus AL and PB2 plus PB, what we can do is draw this kind of diagram. So we would start on the right with 0 volts, and so this would be the standard hydrogen electrode. And then we would have, we would put on the PB2 plus, because that's the next one, which is closest to the hydrogen. And so we would then label that the PB2 plus PB. And then we would also write down the 1.6, the AL3 plus AL. So that's a bit further away, so it's about here. And this is going from positive to negative. And so now you can write on the values. So we have this value here is 1.66, and this value here is 0.13 volts. And so now we can work out the EMF by looking at the difference. So the difference would be here. And so that gives us 1.53 volts, but also that limits confusion between the signs. But obviously you can pick whichever way that you like best. You can either use the equation or draw a cell diagram like this one. Different methods can be used to measure standard electric potentials. So half cells do not necessarily have to consist of the metal immersed in a solution of its own ions. So for example, having copper immersed in copper sulfate with copper 2 plus ions. Any half reaction can be used to create a half cell. If the half reaction does not contain a metal in its elemental state, an inert electrode must be used. So normally this is platinum, as it's extremely inert and it still conducts electricity. And if a gas is involved, it must be bubbled through the solution in such a way that it is in contact with the electrode. So we have two examples here. We have a mixture of Fe2 plus and Fe3 plus. And because these are both aqueous, we've used a platinum electrode, which is solid and inert and also conducts electricity. And then in the second example, we have a platinum electrode again, and it's immersed in a solution containing the Cl- ions. However, the chlorine gas is bubbled through the solution, so it's still in contact with the electrode. We can actually predict the feasibility of reactions using these electrode potentials. So, for example, will this reaction occur? If we look at the table, we can work out what gets reduced and what gets oxidized. So if we connect up this Fe3 plus Fe2 plus half cell to a Cl- Cl2 half cell, we're using this equation and this equation. And we can see that this is more negative, so it has a more negative standard electrode potential. And that means that this gives off electrons and gives them to the Cl- Cl2 half cell. And so it's acting as a reducing agent. And so what's happening is that Fe2 plus is being converted into Fe3 plus and an electron, because this electron is going to the other half cell to reduce it. So in the other half cell, what is happening is how they've written it. So we have the half Cl2, and then that's accepting the electron, which has just come from the Fe2 plus Fe3 plus, and this is going to form Cl minus. And so when we add these two half equations together, we should get the overall reaction. And so we can just add them together like this because the electrons balance out. So we have Fe2 plus half Cl2 plus an electron is equal to Fe3 plus Cl minus plus an electron. So now we can cancel off the electrons. So this is the overall equation. And so from this, we can now say that the reaction at the top will not occur because the opposite of that occurs. So we say that this reaction is not feasible. And that's because when we connect up these two half cells, this is the equation this is the reaction that will always happen because the Fe3 plus Fe2 plus half cell is more negative. Now we're going to have a look at some questions. So for the first question, for the following, draw the conventional cell representations and calculate the cell EMFs. So for A, we know that the half cell with the more negative standard electrode potential is the one which goes on the left. And so this must be the chromium half cell. And then we have to decide between what to put first. Do we put the chromium or the chromium 2 plus ion? Well, the rule is that the more oxidized version of it goes in the middle. So the more oxidized version is the one with the higher oxidation number, and that goes in the middle. So that means that the one with the lower oxidation number goes on the outside, and this is the chromium because the oxidation number of chromium is 0, and the oxidation number of chromium 2 plus, the ion, is +2. So we have chromium, and you've got to remember to write the state it's in as well, so it's a solid. And then we write the Cr2 plus aqueous ion, and because this is aqueous and the chromium is solid, we have to draw a solid line to separate between phases. So then we have the Cr2 plus aqueous ion, and then we draw the salt bridge, which is a double line. And then we do the same with zinc. So we think which one is more oxidized? Well, the one with the bigger oxidation number. And this is Zn2 plus, so that goes in the middle. So we have zinc 2 plus ion, which is aqueous, and then another solid line to separate between aqueous and solid, and then we have zinc the solid. And the way we work out the EMF is if we do EMF equals the standard electrode potential of the right minus the standard electrode potential of the left. And so in this case, the EMF must be equal to minus 0.76 minus 0.91. And so we get plus 0.15 volts as the EMF. And just a quick note that the EMFs should always be positive. So if you've got a negative value for the voltage, then you have done something wrong. For B, we do the same thing. So we think, firstly, which one has the more negative standard electrode potential, and that is the copper. So the copper half cell goes on the left. And now we think which one out of copper and copper 2 plus ion is the most oxidized, and that goes in the middle. And so that means that the copper goes on the outside. So we have copper solid, and then that's separated by a straight line, and then we have copper 2 plus the ion, and then we have the salt bridge, and then now we pick between the Fe3 plus and the Fe2 plus. So again, we think which one is more oxidized, and that is Fe3 plus because the oxidation state is higher than for Fe2 plus because the oxidation state for Fe3 plus is +3, whilst the oxidation state for Fe2 plus is +2. So Fe3 plus goes in the middle, and it's aqueous. So because Fe3 plus and Fe2 plus are both aqueous, that means that we use a comma instead of a solid line to separate them. So we have a comma, and then we have the Fe2 plus. And also because they're both aqueous, we don't have a solid electrode, and so that means we need to use platinum. So now we draw the straight line, because the platinum will be solid. So the platinum always goes on the outside no matter what. And this is our cell representation. So to work out the EMF again, we take away the standard electrode potential of the left from the right. So we would do 0.77 minus 0.34, and that equals plus 0.43 volts. And then for C, firstly we work out which one has the more negative standard electrode potential, and that is the chlorine half cell. And then now we think about which one is more oxidized, so that would be the chlorine, so the Cl- would go on the outside. However, because chlorine is a gas and the chloride ion is an aqueous species, that means that we need another solid again, and so we go to platinum. So platinum goes on the outside, as always, and then now we can write in the chloride ion, and the chlorine molecule. So first we have the chloride ion, which is aqueous, and now we have another line because the chlorine is a gas, it's not aqueous. And then we have the salt bridge, and now we have the MnO4- or the Mn2+, or the H+ to choose from. And so what we do is we work out the oxidation states. So for MnO4-, we have -2 here. So if you times that by 4, you get -8. And we have x minus 8 equals -1. So x equals +7. If you don't remember how to work out oxidation states, then you should quickly just go onto the video about oxidation states and then come back. So the oxidation state of manganese is +7, and then the H+ is +1, and then the manganese ion 2+ is +2. So that means that the most oxidized one goes in the middle, so that means that the MnO4- will go in the middle because the oxidation state is the biggest. So we have MnO4-, and this is aqueous. And then we add in the Mn2+ because it has a lower oxidation state, or oxidation number, and it's separated by a comma because they're both aqueous. And then we also add in the H+, and this is also separated by a comma because it's also aqueous. And now again we need a solid, so we use platinum. So the EMF for this cell would be equal to 1.51 minus 1.36, which equals plus 0.15 volts. So before I move on to question 2, feel free to click off the video and try it for yourself first. So it asks us, would the electrode potential for this half equation change if we used all these different conditions? So the first thing we should spot is that this half equation is actually the half equation for the standard hydrogen electrode. So the normal conditions for the standard hydrogen electrode are that the pressure is 100 kilopascals, or that's equal to 1 atmosphere. The temperature is 298 Kelvin, and also the concentration of H+ ions is 1.00 moles per decimeters cubed. And those are really important facts to remember about the standard hydrogen electrode, and also that the EMF we set as 0. So now let's have a look at the questions. So for A, what would happen if we increased the pressure from 100 kilopascals to 200 kilopascals? So if we look back to the equation and see how many moles of gas we have on each side of the equation, so on the left we have 0, and on the right we have 1. And so what this means is that if we have increased the pressure, that means that the equilibrium shifts to decrease the pressure, and so favours the side with the least amount of gas moles. So in this case it would be the left, so it would favour the back reaction, so the equilibrium would shift to the left. So the number of electrons present will increase. Because the number of electrons has increased, that means that the electric potential of it will be less than 0.00 volts, because it will become the negative. So for A, the answer is it'll become less than 0.00 volts, and that's because if we increase the pressure, then the equilibrium shifts to the left, and so we have more of the reactance, so more electrons. For B, if we use a piece of platinum with a greater surface area, this actually doesn't do anything, because a greater surface area increases the rate of reaction, but it'll increase the rate of reaction of the forward and the backward by the same amount, and so they cancel out, so nothing happens. For C, if we use sulfuric acid with a concentration of 0.5 moles per decimeters cubed, well, because a sulfuric acid has two atoms of hydrogen, that means that actually the concentration of H plus ions in H2SO4 is 1, because there's 2 of them, and so there'll be no effect on the EMF. So for D, if we use hydrochloric acid with a concentration of 0.5 moles per decimeters cubed, well, if we look back at the equation, and if we have now got less, the concentration of H plus ions is smaller, that means that the equilibrium will produce more of the H plus ions, and so it favors the back reaction, and so the equilibrium shifts to the left, so the potential would also be less than 0.00 volts. So got less than 0.0 volts. So the reason is because if we decrease the concentration, then the equilibrium shifts to the left. And so we have more electrons produced. And then for E, if we use a temperature of 50 degrees instead, also the EMF will decrease to less than 0.00 volts, and that's because increasing the temperature will shift the equilibrium to the left, and we can see that from the equation, because the enthalpy change is negative, which means the forward reaction is exothermic. So if we increase the temperature, then it will favor the back reaction, the endothermic reaction, and so more electrons are produced, so the EMF will be less than 0.00 volts again. So we have that it's less than 0.00 volts, and if we increase the temperature, then the equilibrium shifts to the left and more electrons are produced. And also it's useful to remember that the conversion between degrees Celsius and Kelvin is 273. So if you want to go from degrees to Kelvin, then you'd have to add on 273.